Welcome to today's webinar, Deep Dive on AWS Lambda. Our presenter today is Vyom Nagrani. Today with us we also have AJ and Stefano as our webinar moderators who will be engaging with you and answering your questions throughout the presentation while Vyom presents. Vyom, welcome. The floor is now yours.
Thank you. Hello and welcome to the webinar. My name is Vyom Nagrani. I will be your presenter for today. Today we have with us 3 Q&A moderators so we can address as many of the questions as we can. Stefano Biliani is a solution architect focusing on AWS serverless architectures. Vishal and Or are senior product managers on the AWS Lambda team. A little background about myself. I manage a team of product and program managers for AWS Lambda, a compute service that runs your code in response to events and automatically manages the compute infrastructure for you. I hold an MBA from the University of Michigan and have 10 plus years of experience across product management, product marketing, and product engineering. Before we begin, I'd like to walk the audience through a couple of quick items. I hope you can see the Q&A panel on your screen. Please submit your questions at any time during this webinar. Stefano, Vishal, and Or will answer as many of these as time permits in the Q&A panel while I'm presenting. Towards the end of the webinar, there will be a live Q&A session, and I will try to address some of these questions generically on up here as well. Quick note on the Q&A. We welcome all types of questions during the webinar, but the Q&A panel will not, unfortunately, be able to answer any roadmap questions or provide any timelines of upcoming features on AWS Lambda. So we do apologize for that in advance. The intention here is to help you understand AWS Lambda in depth. So we have to give priority to addressing your questions around your technical questions around building serverless applications on AWS. We encourage you to post all feature requests and timeline requests on the AWS discussion forums, where we actively collect customer feedback and votes from these forums. A little bit of context here. I presented a talk called SVR 305 for Lambda best practices at the serverless minicon at reInvent 2016, and hope some of you had a chance to catch that one, and received a lot of feedback from customers to go deeper into the tips and tricks talk of the section of that talk. So this webinar is intended to cover the same content but at a much greater depth, and also address a lot more of the questions through both the Q&A panel and the live Q&A. I will be spending only the first few minutes to introduce the high-level architecture patterns, the benefits, and use cases for AWS Lambda, and will spend most of the time doing a walkthrough of all of the detailed best practices and tips and tricks to follow at the different stages of the life cycle. This content will be most helpful for folks who already have built a few Lambda functions and are familiar with the concept of serverless architectures and event-driven processing. But with that, let me do a quick overview for folks who are new to this concept so that you can also follow along. So the way to think of a Lambda function is it is going to manage the compute resources every time an event is triggered and run your code in response to that event. And therefore, the function which you are going to write is the code which you are, the Lambda function is the code which you are going to upload. And Lambda supports multiple languages for writing that code. The event source is the trigger that actually goes and invokes that function. It goes and tells Lambda, now is when I want you to run this code. The event source could be something which is a change in data state or a change in resource state of things which are built on AWS, or it could be requests to public endpoints, or actually a direct API call made to AWS Lambda. In response to these events, the Lambda functions will run your code, and since you control the code, you can go and have that code interact with anything downstream, whether it's some other database or it's other endpoint which you are going to be talking to. The benefits of using something like AWS Lambda to run your application is that your productivity is no longer focused on managing the infrastructure, but rather is focused on building powerful dynamic and modular applications while AWS Lambda manages all of the undifferentiated heavy lifting for you. Also, this makes it very cost effective and efficient because you are only paying for what you use. There is no paying for idle. In most cases, if you are building something of your own, you have to have somebody who's listening for these events, because at the end of the day, it's these events which you are trying to process. With Lambda, the infrastructure is scaled only when there is work to do, and it is scaled back down, and you no longer pay when there is no work to do, which makes it very cost efficient, not only at low magnitudes, but also at scale. And the third big benefit that we are trying to bring is that you can bring your own code to run inside of AWS Lambda. There's no new programming models, there's no new frameworks, there's no new languages to learn. No, Lambda tries to support the commonly used programming languages available today, and this will continue to extend in the future as we add more languages. And talking of event sources, one big benefit that we have done is to integrate a lot of AWS services to automatically trigger the Lambda functions when something changes on those services. For example, on data stores like Amazon S3, every time a new object is uploaded, edited, or deleted, it will automatically trigger the Lambda function to go and process that event. So instead of having to make two different calls, one for a new object to be available, and then the other one for Lambda to go and run your code, you just have to make that one call for the object, the put object to S3, and the Lambda function is automatically triggered to process that object. The same applies for a lot of the other data stores. As new data is available on Amazon DynamoDB streams or Amazon Kinesis streams, or a new user is created in the Amazon Cognito pools, all of these can trigger AWS Lambda functions. You can also have configuration repositories, where you are storing a lot of state information, where you have things like CloudFormation custom resources, new CloudTrail data being available as S3 objects, a new trigger, a new commit done to AWS code commit, or new logs available on CloudWatch. All of these can also automatically trigger Lambda functions for you. You can also have events or messages such as emails, notifications, or cron events, as well as custom endpoints, where you have things like Alexa or API gateway or even devices being able to trigger the Lambda functions directly. The benefit here is that all of the plumbing is automatically done for you, where you no longer have to go and make these two different calls. And then if you start thinking of what are the use cases where customers are using Lambda today, here's my way of categorizing those three use cases. And of course, this is not a comprehensive list. We always welcome new things which you can build using Lambda. But the way I think of these things is, depending on what the event source is that is triggering the function to begin with, defines what use case you most probably are trying to build. For example, if you have one of the data services like S3 or Kinesis streams triggering the Lambda function, what you most probably would want to do there is to do stateless processing of discrete or streaming updates to your data store. So here you can think of examples like, you have a file coming into S3 and you want to process that file. It's an image which you want to do image transformation on. It's a video which you want to transcode. Or you have a stream of data coming into Kinesis, such as Twitter feeds or social media updates or your user clickstream data, and you want to process that stream of data. So those are examples of data processing or stateless data processing workflows which you can build using AWS Lambda. The other category is when you have an actual, the backend for an app where you have an actual event triggered by a user or a device which is triggering the Lambda function, where you want to execute server-side backend logic for that web app or mobile device, which could be a voice backend built using something like the Amazon Alexa, or you have a interactive web backend or a mobile backend built using API gateway as a front logic. Or you have a device backend where you're going to use AWS IoT as a front end, and that's going to trigger the Lambda function. And the third category is the control systems, where you are trying to respond to state information, or you're trying to respond to create custom workflows. And these could be coming off of things like log processing, or you have CloudFormation custom resources and you want to do something special with CloudFormation. Lambda can become an easy hook to do these types of control systems. So those are the three use cases which we have seen customers build. So from there, let's start diving deep into how you can make the best use of AWS Lambda and what are the best practices that you can follow at each of these life cycle stages. And let's start with the development and testing. So before we go there, a couple of things to understand. As I said, Lambda is a bring your own code. We support 4 programming languages today. We have Node.js, that's JavaScript. We have Java, Python, and C#, and more languages we'll continue to add. The resource model that you think of for the Lambda function is very simple. Now you no longer have to provision anything such as disk or network or CPU or memory. The only thing that you have to worry about is a simple lever. You can think of it as a power of the function, which is represented in how much memory the function has. That goes today from 128 megabytes to 1.5 gigabytes in increments of 64 megabytes. You increase that memory lever and CPU and network are all automatically provisioned in proportion to what memory you have. The way to think of it is a 256 MB Lambda function will have twice the amount of CPU resources and twice the amount of network bandwidth as compared to a 128 MB Lambda function. The use of the Lambda functions or how to invoke the functions also is very simple. There is a synchronous model and an asynchronous model. The difference between these two is that in the synchronous model, think of it as Lambda synchronously responding to the trigger. So let's say you have a web backend which you're building and a user is clicking something and you want Lambda function to respond to that user click. There you have to send it as a synchronous request where the Lambda will not respond till the execution of the whole Lambda function is completed. And on completion, the return value of Lambda will be actually returned all the way to the invoking client, and the client can use that response in the next line of code. The asynchronous mode is more useful for things like data processing, where you want to do the fire and forget method. Here, you can invoke the Lambda function asynchronously, and a lot of AWS integrations like S3 and SNS are all asynchronously integrated. What this means is that when the invoke comes in, you will get a 202 response back from Lambda saying, I have now accepted this message. And Lambda will internally queue that message. Your client application can then continue doing its own work. But remember, it's not going to get any response value back from the system other than a 202 message accepted. Lambda will then read off of that queue and then process your messages as time permits. The reason this is much more beneficial for data processing is you can start uploading huge chunks of data into the system, and you don't have to worry about any sort of scaling limits or your throttle limits on the system, which we'll talk about in a minute. Lambda will automatically absorb all of these incoming requests and then process as time permits. And of course, the use is always other AWS services that we talked about. The other thing to remember during your development is that the Lambda functions are stateless, which means you have no affinity or even access to the underlying infrastructure. So you can no longer do things like let me SSH into the instance and let me SSH into the function and find out what's going on. You have to persist all of the data from your functions, from individual invocations of your functions to some external storage. You can do things like an S3 backed or an Amazon DynamoDB backed state or data that you can store in there. And we can talk about other tips. I'll talk about a couple of other tips during the presentation of what more can you do to optimize that performance there too. So then let's look at the anatomy of a Lambda function. Now that you want to create a Lambda function, what are the things? The first is that a Lambda function is the only unique part of the Lambda function versus something running on your own server is that you have to define a handler function. And this is just declaring any function as the handler. Whenever Lambda receives an invoke, this is where Lambda will begin execution of your code. So this just defines what the entry point of the function is, because here, remember, you are going to enter and exit the function multiple times, and it's not a service which is effectively running all the time. Lambda is the service. Your code only executes for each request. The actual request itself, the event object, comes as one of the parameters which is passed to this handler function. There is a predefined object format for all the AWS integrations and event sources, and you can look at our documentation and see what that predetermined format is. Java and C# support both POJOs or POCOs as well as a stream input-output. So if you want to send in a custom stream, then you can go in and send that request, and you own typecasting that into individual variables which you want to use. The other parameter handler function is the context object. Now the context object gives a lot of control on different properties which you can use. So A, it gives information about what the requesting object is. B, it gives information about the context in which, the environment in which the function is running itself. So there are different properties which you can use to optimize things on your Lambda function. For example, you have a parameter called get remaining time in milliseconds, which is a method you can call from inside the Lambda function, which will return how many milliseconds are remaining before your Lambda function times out. And you can use this property for making custom decisions, whether you want to continue processing or you want to fork out to a different Lambda function, in case you feel that you won't finish the rest of the processing in the remaining time. It also has things like the identity, which tell you information about the function itself, or the AWS request ID, which is a unique identifier for each incoming request. And you can use that to build things like idempotency into your system. You also have things like invoked function earn, which gives the property of what is the earn which is invoked in the first place. Now, was it a specific, if you have the same code shared across different functions, you want to know inside the code which function am I actually running in, and you can use this property. The client context also gives an information thing for things like, especially for mobile devices when you're calling the Lambda function, of information about the device itself. So you can do custom responses using this client context on, depending on the size or the resolution of the screen, you might want to send in a different response. And the log stream name allows you to identify where your function is being logged in case you want to go and correlate your logs at the end of the function execution. Now, in addition to, so what I talked about earlier was the function itself and the running of the function. Now let's talk about what the metadata each function has that you can configure on top of the function. The first important one I want to talk about, in addition to these three, of course, there are others like the function name and the function function properties. But these are three other metadata objects which I want to talk about in a greater depth. The first is the VPC config. This allows you to configure your function to be able to access resources inside your own VPC. Remember, this is not a security feature per se. Lambda functions, even if you have not configured the VPC config, do run inside a VPC. It's just that at that point, Lambda manages that VPC. And therefore, if you want to access private resources inside your VPC, such as an Elasticache cluster or a private endpoint which you want to communicate with, you can use this VPC config to enable that private communication. What happens when you configure this is you have to provide a security group and a list of subnets. AWS Lambda will then follow the rules of that security group and create private IP addresses inside that subnet and connect those ENIs, use ENIs to, which of course Lambda will auto-create, to be able to connect inside your private endpoints. If you want internet access in addition to these private communication channels, then you can use a NAT gateway inside your private VPC to enable this access. Internally, what we do is we will follow the subnet, the security groups, and therefore anything that the security group allows, we will allow to pass through in the context of these private IP addresses. The other configuration is the dead letter config. The dead letter config allows you to build a effective redrive policy for requests that AWS Lambda cannot process. The AWS Lambda has its own retry policy for asynchronous invocations. Today, the redrive policy, the dead letter config, is available only for async invocations, whether it's a direct async invoke or it's an integration with AWS services like S3 or SNS. At the end of the redrive policy, Lambda tries a couple of times, but if none of those executions fail, you can configure a dead letter queue or a SNS topic to which the original invoke is just sent back again. So the whole event object is pushed to this dead letter config which allows you to choose your own retry policy. You can send it to another Lambda function. You can queue it up and read it on your own. But what this allows you to do is to build robust functionality and get that high level of fidelity on the system, where you know that even in case my Lambda function fails, I'm not going to lose any data. That data comes back to me and I can choose to retrieve it. The third one that I want to bring your attention to is the environment metadata. Environment variables for Lambda functions enable you to dynamically pass settings to your function code without having to make any changes to the code itself. So environment variables effectively are key value pairs that you can create and modify as part of your function configuration, either using the console or through the standard APIs and SDK. AWS Lambda then makes these key value pairs available inside your function code using standard APIs supported by the language, such as things like process.env for Node.js functions. So you can use these environment variables to help libraries know what directory to install the files in, where to store the outputs, store connection settings, logging settings, log levels, parameters like those. And by separating these settings from the application logic, you don't need to update your function code whenever you want to change the function behavior. All you need to do is change the metadata of the code, which is often much more easier to do. And also, these environment is encrypted with a specified KMS key on the server and is decrypted inside the Lambda function on initialization. And therefore, you can be sure that these environment variables which you're passing in are also secure. I do want to draw your attention to some of the AWS Lambda limits, and I'm not going to walk through each of these individual limits, but the thing to notice is that there are certain constraints within which you need to build and deploy your Lambda functions. There are limits in terms of how long each request can run, how much disk space each request gets, how big of a payload you can send into the system, how big of a dead letter payload you can respond. There are also deployment limits on how big each individual size of function can be, which is 50 megabytes compressed to 50 megabytes uncompressed. There's a limit on the total number of the total size of all of the deployments put together in each region for Lambda. So a lot of these are things which you need to architect around. But the one which I do want to call out is the throttling limit. Like, I'll discuss how throttles work. But effectively, Lambda gives you this safety knob on top of your execution that says, at any given point in time, I do not want more than a certain number of functions to be executing. And this allows you from accidental or runaway usage. If you have configured a public endpoint and which is going to be being responded by a Lambda function, you don't want to flood your downstream database. You don't want to have a huge bill because somebody started calling that endpoint without your knowledge. And this limits the terms of at a given point in time how many functions are running, which you can think of as the concurrent executions of Lambda. As a default, this is set to 100 when you create the account. However, this is the one limit which is flexible, which means you can ask AWS to increase this limit for you. And we have customers who are running, a huge number of concurrent functions in parallel. So, if you ever hit this limit, just let us know and we can always increase this limit for you. The other thing I want to talk about is the container model. So let's think about how the Lambda function is running realistically. Each execution of your Lambda function is a container which we are creating and managing all of this for you. So you never have to think in terms of creating, managing, deleting containers. You only think in terms of what the function is running. But it's helpful to know what's happening on the back end. For example, we try to reuse those containers. Now, whenever there's a new request coming in for the first time, we will create the infrastructure for you. But then we will try to reuse that containers across invocations for the exact same function. So more copies of the same function may reuse the same container. You can actually make that, put that to your own benefit. Anything which you declare in your Lambda function outside the handler effectively will run only once, because the handler function is the only thing which is going to go inside of your execution for the function run. So you can start declaring things inside this code, and those will be effectively treated as a global namespace, which can be shared across Lambda function across different invocations. Same thing, you can add the disk content of the /tmp. That also stays across Lambda functions. Any background processes or callbacks which you have initiated, even if the function actually terminates, these background processes will continue to run. So you can opportunistically make use of this. If you want to load additional libraries, or you want to cache some static data or create database connections, all of this you can do outside of the handler function, or you can store to a /tmp, or you can put to a global namespace. And you have effectively created a very local, very fast cache instead of having to write to the external storage service each time. Now note, you cannot rely on this, which means you cannot go in and say, I will write to this and my next invocation actually relies on this being available the next time. Since you don't have control on the container reuse, you might just lose that data. So you have to store only cache data in there and not the actual data itself. The other thing which a lot of customers have talked to us about is a cold start. And a cold start effectively is the time needed for Lambda to bootstrap a new container when the Lambda function is invoked for the first time. And while we have seen cold starts are extremely rare on the system because our container reuse aims to capture as many retries as possible, there always will be times where there's no traffic for a long time, and then suddenly you have a burst of activity. And obviously that's going to have to spin up new infrastructure for you. So while you can't absolutely eliminate these, there are a bunch of things which you can do to reduce the cold starts. So first is that, remember, more memory means faster performance. Faster performance means there's going to be a lower startup time. The amount of things that the function needs to do to start up can be done in a shorter amount of time. So if you increase the memory, you can effectively get a faster response to cold starts. And since Lambda is built in terms of GB seconds, the memory you allocate times how long it takes to execute your function. If more GB is going to mean fewer seconds for execution of your code, you might actually get faster performance without having to pay anything more for that. The other thing you can do is that a smaller function zip, that the smaller the code you upload, the faster it is going to be able to load it. So try to remove all unnecessary binaries or unrequired code from your function whenever you are whenever you are loading the function. Because remember, even if you are not going to actually use that library, we are going to have to load it, which is going to slow that down a little bit. And the third thing you can do is, opportunistically, you can figure out that some languages just work better than others in terms of cold starts. Now, whenever you are booting a compiled language, there is that additional time that goes in. For example, if you're running a Java code, there is the time. It's a property of the language where JVM doesn't boot as fast. Same thing with the C#, where we don't have to boot the whole .NET Core CLR. On the Python, which are interpreted languages, there is not much of loading to do. The first line of code actually runs really fast. So if possible, you can start moving to some of these languages if cold starts are a real problem for you. And we have seen that the cold starts for Node and Python are actually much lower than the cold start for Java and C#. And it is on our roadmap. Now we are working on making these cold starts better for you anyway. So this is all of me. The other thing to remember is the execution environment. Now, behind the scenes, Lambda is running a public Amazon Linux AMI version with a standard Linux kernel version, which is mentioned here. But note that these things keep changing. Since this changes over time, we will start upgrading. One of the benefits of Lambda is you don't have to manage these patching and upgrading of these systems. If there's a new AMI, if there's a new kernel version, if there's a zero-day fix, we are going to patch that for you. So just make sure that you check the latest supported versions on our documentation. But the benefit that you can get out of this is you can compile native binaries against this environment. So effectively, you're bringing your own runtime. Any language which you want to run, if you want to run something in Perl, you can go and compile that against this language and then bring that entire binary. If it runs against this Amazon Linux version, it's going to run against as a Lambda function. So we have customers who are uploading custom binaries, native binaries, even things like an FFmpeg binary, where you can package that as your Lambda function, fork out to that process, and therefore effectively now you're running FFmpeg as a Lambda function. Also, there are some libraries which we have made available as a default. Now we have a few ImageMagick Node.js wrappers and native binaries. We have the different versions of the JDK, .NET Core, SDK for different languages. Some of these are already inbuilt. Some of these you might have to bring in yourself when you are compiling the functions. For example, we don't have a Java SDK in here because Java SDK needs to be compiled with the code into the jar when you're uploading it. While these binaries are available as a default, in case you have a dependency on a specific version of the SDK or library, you can bring in your own custom SDK. And again, remember, these libraries also change over time. So make sure you're looking at what library is available if you're taking dependencies on specific SDKs. So that was building the Lambda functions. Now let's talk about deployment and ALM. When you're building the deployment package, you can bring in either a zip file or a standalone jar or DLL if you're running Java or C# functions. It's always a zip file for the Node.js and Python, but the other ones also include other capabilities there too. You can start packaging all of your deployment or your dependencies and libraries, even your actual executables or binaries into that zip file. And we have different tools available for packaging those libraries. For example, you can use npm for Node, pip for Python, Maven or Eclipse IDE plugins for Java, or you can use NuGet and Visual Studio plugins for building those C# dependencies and libraries. And each of these languages have their own mechanism of where each of these dependencies should be. And most of them have these dependencies at the root level, but in Java you can have some required jars in the lib directory as well. And in most of these cases, if you're using the AWS tooling, you don't have to worry about all of the dependency management. It's kind of taken care of for you. Managing continuous delivery is something which a lot of customers have talked to us about. The recommended CI/CD solution which for building serverless applications is something which we recently announced at reInvent. And that is to use code commit as your source repository, code build to package your source code, code pipeline to bring it all together and to orchestrate that application deployment, which will then internally call CloudFormation to actually deploy your application, which we'll talk about in a bit. So the pipelines can pick up the source code changes from a repository anytime something changes, build and package the application by running it as a code build build process, and then push the new update through a series of stages and enable you to run integration tests to ensure that all of your features are intact and backward compatible on each stage. The pipeline can also be configured to pick up your code when it's committed to the source repository on code commit, and then proceed to start the deployment for each stage. And then again, before moving to each stage, the pipeline can actually execute integration tests so that if the test fails, the pipeline can stop. And you can go through the couple of demos which we have put up in a blog post which we have on how to build up this CI/CD solution on AWS Lambda. So while that's the recommended solution which AWS as AWS we are offering, that you can start building your Lambda functions with. You can have GitHub to replace your source repositories. You can set Jenkins to go through that build and test processes, and you can integrate. We have Jenkins plugin which will allow you to run these continuous integration tests on your. And we have other deployment partners such as CodeShip, which allow you to now deploy Lambda functions. Customer complete DIY Lambda itself. Lambda Now, when build the function, and then we often click which of these in your environment. In terms of deployment tools, one thing which I'd like to talk about a little bit depth is CloudFormation AWS Serverless Application Model, or the AWS SAM. You can deploy and manage your serverless applications using AWS SAM, which is effectively a specification that prescribes the rules for expressing serverless applications on AWS. This specification aligns with the syntax used by CloudFormation today, but also natively within CloudFormation supports a subset of resource types referred to as serverless resources. So these resources make it easier for customers to use CloudFormation to configure and deploy your applications using the CloudFormation API. So there's nothing except for the subset of resources which such as used to a serverless application. So these includes APIs, the Lambda function itself, a dynamo table, and the mappings between each of these components, as well as some custom things such as environment variables or state variables. So in order to deploy your application, you simply specify these resources you need as a part of your application, and any other IAM policies or permissions which are required. All of this can be written in JSON or YAML. You can package these deployment artifacts and then deploy the SAM template. The SAM template effectively is going to, behind the scenes, convert these simplified resource models into a traditional, standard CloudFormation description. And the specification, of course, is available under Apache 2.0 as an open specification, so AWS partners and customers can adopt and extend this with your own toolkits. So that was SAM, and there are a bunch of third-party tools and first and third-party tools which are built on top of AWS CloudFormation. Chalice is one good example which AWS has introduced. Chalice is a Python serverless microservice framework that allows you to quickly create and deploy applications that use Amazon API Gateway and AWS Lambda. There it supports these two services. And while it's currently in preview, it's offered both as a CLI and an easy-to-use API. Chalice is focused on using a familiar decorator-based API written in Python that can allow you to deploy your Lambda and API Gateway solutions. So you can think of it as a Flask bottle for serverless APIs. The goal is to make writing and deploying these type of applications as simple as possible. And it's available on GitHub, so we do encourage you to go and have a look and see if this works good for you. In addition, there are a lot of third-party tools such as the serverless framework, the Apex framework, or the Deep framework, which offer similar functionality with much more focus on integration into your environment. So you can have a look at some of these frameworks and see if those work better for you too. So now that we're talking of ALM, I want to talk a little bit about how function versioning works. So versions effectively are immutable copies of your code and configuration. So while aliases are mutable pointers to these versions. The way to use these two together is whenever you are developing a function, it's always against a $latest version. However, you can at any point in time go and create a snapshot that says this version of development I want today as a individual version which I want to call independently of what I'm developing on. And then each version in alias gets its own ARN. So you can invoke either the function itself, which will always call the $latest. You can invoke a specific version. So you can say in lambda.invoke my function :17, and that will invoke version number 17. Or you can create aliases and say invoke my function :prod. And behind the scenes, you can choose whether you want to point prod to 17 or 12 or $latest. And this makes it very easy to enable rollbacks or stage promotions where the behavior for the client is locked. The client always calls my function :prod, but behind the scenes, as you develop, that can go from 17 to 18 to 19, and the client never has to change. So then let's talk about security and scaling. So in terms of how the Lambda function executes and what resources or permissions you have to provide, you have to think of the two different models for for how Lambda functions are invoked. For most of the synchronous and asynchronous calls, Lambda functions use this push model where the upstream service is actually invoking the Lambda function. So in this case, you can use a resource policy where you grant permissions to your Lambda function which determine which service or event source can invoke your function. So the resource policy is applied to the Lambda function, which makes it easy to even grant cross-account access permissions. So you can say, as this Lambda function, I allow an S3 of this other account to be able to invoke me. And that therefore, every time there's a new file in that S3 bucket, it can go and trigger the Lambda function. Remember, this is only the permission. The resource policy only grants the permission. The actual hookup of the event source you have to do either on Lambda or S3 consoles, which is a different step. But if you do it on the console, if you hook up the event source on the console, it will automatically create this resource policy for you. The other thing is the pull model. For streamed event sources, which is Amazon Kinesis streams and Amazon DynamoDB streams, the stream is not pushing the data to Lambda. Lambda is actually going in and polling these event sources. So here, you need to give permissions to grant your Lambda function to go and read off of these event sources. Here, this permission is applied in terms of an IAM role. So you give an IAM role policy that allows Lambda to do a Kinesis get object from the stream or a DynamoDB get record. So let's talk about concurrent executions and throttling. So we talked about the default limit of 100 concurrent, which can be modified. But the way concurrency is determined is that for most other event sources, the concurrency effectively can be calculated as the individual request rate of how many requests are coming in per second multiplied by how long each function takes. For example, if you have a 5 files per second coming into the system and each file processing takes 3 seconds, then if you look at inside the system, there will be 15 Lambda functions which are running behind the scenes at any given point in time. So this 15 is the concurrency of how many functions that are running there. For stream-based event sources, because we have to follow order, we will not fan out that way. In most cases, Lambda will fan out to meet the rate of incoming requests. But for stream-based event sources, the concurrency is limited to the number of shards per stream or the shards per table on the DynamoDB streams. That becomes the unit of concurrency. For example, if you have a 20 shard stream, then there will be 20 functions, Lambda functions in concurrent, which are reading off of that stream. Even if you have a lot of data, it's not going to start reading faster by creating more Lambda functions, because then we lose order. So the throttling behavior actually will change based on what type of request is. Now for stream-based event sources, even if you do get throttled, it's not going to make any difference. The data is going to stay in the stream, so that gets automatically retried the moment you are no longer throttled. For asynchronous invocations, in case you get throttled because there is not enough concurrency for you to process your incoming data, that data starts getting queued and it will be automatically retried for up to 6 hours with a delay between retries. So we will automatically manage all of that for you, and this doesn't count towards an error. This only counts towards a throttle. However, for synchronous invocations, since there is no concept of let's wait and process this later because there's a client actually waiting for a response at the other end, we will send a throttle request, a throttle response called a 429 error back to the client and let the client decide what you want to do in terms of retries. Now, once you get throttled, for the client, and actually an error and a throttle might not be too different, except that for a throttle, it might try to retry because a few seconds later, that throttling might have gone away. Therefore, in most cases to consider when scaling, a throttle is not an error. Now, for both stream-based and for asynchronous invocations, a throttle just means a slight delay. So if we expect a sudden spike in demand, then consider using asynchronous invocations if possible. If there is no client that is waiting at the client end, then you can just use asynchronous invocations. That way, even if you do get throttled, Nothing's really happening. Just instead of a few milliseconds later, the code is going to execute a few seconds or a few minutes later. But it is going to run, because Lambda is going to automatically retry that. And if you know that you have upcoming scale events which is going to require a lot of scaling, then proactively reach out to AWS support to increase your throttling limits. Also, on the upstream service, try to implement some sort of retry or back-off algorithm, especially if you control the client application. Also, make sure that your downstream setup keeps up with Lambda. Now, we've heard a lot of customers say Lambda actually scales too fast for me to handle my downstream setup. Especially if you're doing something like databases, relational databases. You might want to limit that concurrency of how many functions can go in and connect to your database, because the database will not take beyond a specific number of connections, especially if it's a relational database. So make sure that your Lambda scaling and your downstream scaling are all aligned. Otherwise, what will happen is the Lambda functions will start timing out because the downstream database never returned your connections. And what could have been a simple scaling check ends up becoming an error. So then let's talk about debugging in operations. So we talked about throttles, but specifically for errors, there are two types of errors, and the retry policy for errors is different than the retry policy of throttles. The types of errors are normally 4xx errors, which are client errors, which could be things like an invalid parameter value, a resource not found, I'm just trying to invoke a function which doesn't exist, a request too large, which might be, I'm sending in a payload which is greater than 6 MB and therefore cannot be processed. Or they could be things like 5xx errors, which are server errors, but could still be fixed by the admin. The most common 5xx error we get is the 502 error, which is an EC2 ENI management error, which you would see only if something goes wrong inside your VPC config of the Lambda function. And this can be fixed by the admin by either asking for more ENI, asking for higher ENI limit, or cleaning up some of your ENIs. Now the retry policy for the errors, as I said, is different from the throttle retry policy. If you see an error on a stream-based event source, this is the one which is the same. We will just continue to process the data because we have to process the data in order. We cannot skip over a record because it failed. So we will just continue to retry the same event till we continue to find an error. For asynchronous invocations, if the function fails, we will retry 2 extra times. So the original plus 2, so a total of 3 times. And then we will publish that original event to the dead letter queue if you have configured that as a dead letter policy. For synchronous invocations, any error, we will just send the error code and the error message back to the client, and again, let the client decide on what they want to do with that error. For tracing and tracking of events, now we have an upcoming integration with the Amazon X-Ray. So AWS X-Ray helps developers to analyze and debug production distributed applications, such as those built using a microservices architecture. X-Ray effectively can allow you to understand how your application and all underlying services are performing, and also identify and troubleshoot the root cause by diving into an end-to-end view of the request as they travel through your application. So let's say if service X calls service Y, calls service Z, then you will see that entire path when you are creating your X-ray traces. And X-ray effectively can create a map of your application's underlying components for you. And you can use that to analyze the applications, whether it's in development or in production, and it's your choice what type of applications you are doing. With the integration with X-ray, AWS Lambda is going to get you the visibility of things like a dwell time, the number of retries, the latency, what errors caused, also a detailed breakdown of function performance, including calls made to downstream services and endpoints. And this is coming soon. X-ray currently is in preview, and you can go and sign up for the X-ray preview. This integration is coming soon too. The other thing is the integration with AWS CloudTrail. So all calls made to Lambda are effectively logged to CloudTrail. So you can create these requests. CloudTrail delivers all of these as a log file to Amazon S3. And it also has things like what source IP the request was made from, who made the request, what are the permissions, when it was made. So you can use all of these on Lambda to track what all changed. And remember, it's only the control plane APIs. So for example, there is no versioning or aliasing, or the invoke APIs aren't sent to CloudTrail yet. But anything which is creating a function, changing the configuration, metadata, creating new policies, changing the event source, all of these are tracked into CloudTrail. So you can see what's going on and trace the history of your application. And of course, logs and metrics. Now we provide logs as a default, where every request will create a set of logs. Every log will have a start, end, and report entry in CloudWatch, and plus all user logs. And then depending on the runtime, you can choose what user logs. So we have mapped some of the things directly into user logs, so you don't have to call the CloudWatch APIs. For example, in Node, you just say console.log, and that goes into the CloudWatch logs along with the rest of the log entry. Additionally, we have default metrics for free. That is the number of invocations, how long the functions ran on average, if a message gets throttles or errors, with new metrics coming in soon. But remember, these are just the ones which are default. You own the logs, so you can add any sort of custom logging that you want to in there, and then you can debug your Lambda functions based on the logs. Plus, you can create custom metrics too. Now remember, it's your function code. So adding a new metric might be a very simple thing to do for you. For example, you can also start differentiating between a ops-centric metric and a business-centric metric. An ops-centric metric would be what's given as a default, is the number of invocations of the Lambda function. A business-centric metric could be something like, I will parse the client context from the functions, and I will create a metric on how many mobile devices are calling me versus web-based requests are calling this function. So that's a business-centric metric, which we have no access or insight into, so you can create on your own. Since it's your code, creating a metric or publishing a metric literally is one line of API call being made to the CloudWatch metrics. So with that, I'd like to call out a couple of things as a takeaway. And the main one is that now Lambda is now becoming a core component of the platform that AWS provides to develop serverless applications. Lambda forms that core compute offering in the serverless ecosystem with a lot of other AWS services that you can use very easily with the Lambda functions. So as next steps, I'd urge you to stay updated with what the AWS Lambda announces on the compute blog, and also to check out our detail page for more scenarios which you can start leveraging. And of course, your questions, comments, feedback, votes are really helpful to us. We as product management team, we do prioritize our features based on what we hear from customers. So please do send in your feedback using the AWS Lambda forums. That's all I have in terms of the slide context.
Great. Thanks a lot, Vian, for a great presentation. And I'd like to thank the moderators for answering everyone's questions. If you have any comments on our previous and upcoming webinars or suggestions on the topics you wish AWS will cover in future webinars, please drop us a line at aws-webcast@amazon.com. Your feedback will help us to improve our webinar programming. Thank you for taking the time to join us today. Enjoy the rest of your day.